All right, if we want to find the area of a polar graph, we want to keep in mind that a polar graph is created by spiraling out or spiraling in. And I'm going to draw some little lines from the pole to the curve. Doop, 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 doop. So what I want you to see is, instead of rectangles, which we needed back when it was y equals f of x, when it was y equals f of x, we found area through rectangular Riemann sum approximations. When it comes to polar, we use areas of a sector of a circle. And back when we were dealing with the rectangles, we chopped the x-axis up into tiny little pieces. This time, we are taking theta and chopping theta up into tiny little pieces. So that means that when we get to the point of the formula for the integral, it's going to be with respect to theta. But first, what is the area formula of a sector of a circle? In radians, mind you. The way I always think about it is I have a certain percentage of the circle that sector is. I know the area of a circle is pi r squared. The percentage of the circle is theta out of and then radians would be, yep. So theta, come back to me, theta divided by 2 pi. Mind you, this is only if you are doing radians does the formula come out this nicely. And we get, drum roll, are you ready for the reveal? Whee! 1/2 r squared theta. Yeah. But the theta is going to turn into d theta. So what you're really going to have to remember is just 1/2 r squared. Not too bad. And keep in mind that you can think of it either way, but realize that you will be given r as a function with respect to theta, or r could be a constant. If r is a constant, then you could use area of a sector formula instead. And then I've got some possibilities of problems that I will go through with you. Not going to be able to get through all of them. But what I want to do is talk you through graphing while talking you through how to set up an integral for area. You're not going to do any integration by hand with polar because most of them require an integration technique that is not on the AP test that we will be learning after the AP test, since we have an entire month and about a month and a half almost after this AP exam, which I really wish it was later, give us more time, but oh well. That is not our boat. Gotta float in the boat you are in. Ha ha ha. Okay, yes, spring break is upon us, and I am just delirious with, yeah, no other explanation. All right, so let me make sure that we need to take a look at the graph of 21. We have to look at this graph. So what I'm going to do is talk to you about creating the graph based on, do you know the Cartesian graph? So we have sine is multiplied by 2. So stretch. And then everybody moved up 1 unit. So the sinusoidal axis is 1. And then the amplitude is 2. And then we draw our lovely sine graph starting at the center and first going up, whee, and then going down, whoa. And because x is not multiplied by anything, not added or subtracted with anything, we've got our typical 0 to 2 pi. Halfway there is pi, 1/4 of the way, and 3/4 of the way, and an additional pair of very important points, VIPs, very important points. We need to know anytime the radius is equal to 0, what angle are we at? So when you are dealing with that, I want to point out that we are actually dealing with this polar function. We are trying to solve for when r is equal to 0. So that gives us sine theta being -1/2. When it comes to the unit circle, sine is telling us y coordinates among the unit circle. And the special y coordinates are positive 1/2, root 2/2, root 3/2, negative 1/2, negative root 2/2, negative root 3/2, on top of positive 1, 0, and -1. -1/2 puts us at pi/6 beyond pi and pi/6 prior to 2 pi. We've got our angles. Now we're going to look at the graph in polar. This gives us a nice continuous chart-like thing on how to graph. When my angle is 0, my radius is 1. At pi/2, my radius is 3. And then I come back to a radius of 1 when I hit pi. And then I want to realize that it will spiral out. Whee! And then it will symmetrically spiral back in. Whoa! Then, as I go from pi, the first thing that happens is I spiral into the pole by the time I reach 7 pi/6. So 7 pi/6 is where it gets sucked in. Now, trying to graph this, I need to zoom in a little bit. Well, that's a little lopsided, isn't it? Okay, the perfectionist is saying not good enough. Maybe that's better. I'll show you the Desmos version in a bit. Now, I have a negative radius between 7 pi/6 and 11 pi/6. That means I'm not going to see the graph occur along here. I'm going to see it occur between these two. Are you ready? Here it goes. We just came out of new, and come on. And then from 11 pi over 6 to 2 pi, we finish up with some symmetry. And what we have is a limousin with an inner loop, otherwise known as limacon with inner loop. And I'm going to grab you that graph. That was which equation? Here. That was 1 plus 2. I'm bringing it over. Much curvier than what I drew, but pretty. Know that something is called a limousin whenever its function has addition or subtraction with a number, and theta has nothing done to it. So basically, we get a limousin anytime that we have a vertically translated sine or cosine graph of whatever amplitude. But again, it's just theta in there, and it creates an entire family of limousins. If the amplitude is more than the translation, then you're going to have an inner loop. But you could have the translation be more than the amplitude and not have an inner loop. And there are a variety of cute little graphs that come about. The most famous of which, well, I don't know if it's the most famous, but maybe it is, the cardioid. The cardioid happens when the amplitude and the vertical translation are the same, absolute value the same, because that's when it will touch the x-axis and bounce right off. And that creates that sucked into the pole, spit out of the pole cardioid. I know the word, but I can't think of it right now. There's a word for when it does that. Cusp. Creates a cusp. So anyway, how do I set up an integral that will find the area of that inner loop? Really, the big thing with you drawing a graph is to understand where the curve exists. And a lot of times I set up my integrals based on the Cartesian graph that I'm more familiar with, because I can see really clearly with the Cartesian graph that the inner loop occurs between 7 pi over 6 and 11 pi over 6. However, if I'm looking at the polar graph, I could be deceived because it looks like it's occurring from pi over 6 to 5 pi over 6. But if I look at area from pi over 6 to 5 pi over 6, it's going to find me this area. And that's not what I wanted. So it's always looking at what is the angle that creates the graph. On the AP, would they give us the picture graph? Yeah, they pretty much always give you the graph. I have noticed that they don't seem to expect you to know the polar family of graphs. You're better off if you do know them. It's highly unlikely that you will graph on the AP exam. That is unpleasant grading. It's very rare that they ask you to do any sort of graphing on the AP test, but they do sometimes. very, very occasionally, you're more likely to have to draw a slope field or draw a solution in a slope field, which are on their own that much more difficult to grade than you just writing out actual math in words versus a drawing. Because a drawing, they've got to go like, well, is it steep enough? I don't know. What do you think? Is that steep enough? Yeah, not pleasant grading. Usually they will give you the graph, but I will say it definitely helps to be familiar with the graphs. But even more so, it's very important that you're aware of how the graphs are created. It helps to understand what is going on. Anyway, all I did was I looked at the endpoints of my integral. What's the formula? The formula is 1/2 r squared d theta. My r was 1 plus 2 sine theta. And then I'm not going to solve the definite integral. I'm just going to say you've got it. If you want to find the area, you can plug it into your calculator. Now, here's the thing. You're going to have multiple choice questions. Those multiple choice questions may not have this integral as one of your possibilities. It may look different. You need to understand the symmetry that is involved. Maybe I should throw Desmos out here instead of my graph. So the symmetry involved of this inner loop. Can you think of another way to write that integral? Recognizing the symmetry as I go. What? How does the loop factor into the area? This was an issue where they asked you to find the area enclosed by the inner loop specifically.
So if it asks for the whole thing, would it just be the same whether it had the inner loop or not?
Let me tell you that they will not ask you for that with something that has an inner loop. It's too confusing. If they asked you for area and you had a limacon with an inner loop, they would only ask you for area in the inner loop. That'd be the whole purpose of it. Otherwise, they might give you a rose curve like number 18 and ask you to find the area of the region enclosed by one loop or one petal of that rose curve. And if you understand how to graph the Cartesian graph, a loop is created between an r equals 0 and another r equals 0. Honestly, I find it easier to set up the limits of the integral by looking at the Cartesian graph. If I graphed this one in the Cartesian format, I would have sine graph going wee, wee, all in 2 pi over 3. Ha, 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 ha. Yes, spring break is upon us. I'm very slightly numb from the craziness of the last few weeks and happy and excited and exhausted all in one, which I'm going to guess you guys are in the same boat, maybe even a worse off boat of, I just took tests. I still have to grade them though, but I'll be able to get that done quickly. Anyway, and I will get those up. I want to try and get your grades up this weekend so that you know, including the ones that I didn't get graded before. Oh my gosh. Yes. Yes. So tired and excited. All in one. Oh, yeah. I never test the day before a break because of the "my brain is on break already" comment. And since yesterday, which I know. Yeah. So right now, you are just having fun watching Polar because Polar is beautiful. It's so smooth. You know, I'm so tired of those boxy things with the X's and the Y's. Anyway, if you realized what was going on here and you needed to find the area enclosed by one loop, you would just need to realize, well, 0 to pi over 3 takes me through one loop. So if I integrate from 0 to pi over 3, 1/2 r squared d theta, where r is this, then I'm good to go. Voila. But I come back to the question, symmetry. How else might this be written due to symmetry? Yeah, I can put in office hours today to take a look at this. My only concern is over the week you might lose everything that you've gained. Are you ready? While that could be an option, they're more likely to do the following. If I stop at 3 pi over 2 and double the area, I won't even see a multiple there. So you would only see this. Most likely this is what you're going to see in the multiple choice answer, but it could also be 3 pi over 2 to 11 pi over 6. And let me go back to the picture of the symmetry. 3 pi over 2 is halfway in between. And then for the rose petal, it could be, if I multiply by 2, what do you think they're most likely going to change? Yep, most likely this is going to be pi over 6 if they double it. But if you get how the symmetry works, you can figure out however they decide to put it. So it's important that you understand the graph for that sake. Now, we are ready to graduate already to area inside two curves, and it could be inside one, outside the other, or it could be inside both. Those are the two things that could be asked of you. I'm going to make sure to hit 23 and 25 and just do both. So let me explain the directions. There's area inside first curve, outside second curve, and then there's area inside both. And I'm just going to do everything in one. So I'm going to take this because I need to talk about the graph, some of the graph issues going on there. There are others I would like to do, but our time is limited. Okay, So you're trying to graph this. Start off with Cartesian, and 2 cosine theta goes wee, wee. And it is just theta, so 2 pi. Amplitude is 2. And I will tell you that I find it so much easier to graph if I extend and graph from just graph one loop from where the radius is 0 to the next time the radius is 0. So halfway is pi, halfway again is pi over 2. That makes this negative pi over 2. I'm literally drawing a graph from negative pi over 2 to positive pi over 2. And I'm going to grab this grid. So realize that I'm coming out right here, and then I'm going to get sucked back in at pi over 2. I am staying in between those two. And I go all the way out to 2. So I'm going spiral out, spiral in. Now, it's valuable for you to be familiar with what shape that just created. And to figure out what shape it just created, I'm going to go back to something we did yesterday, the triangle. If you draw an XY plane, plot a point right in quadrant 1, and then draw our theta and XY, you've got your triangle. If I want to convert this from polar to Cartesian, I told you yesterday that I recommend you look at your trig functions first and substitute in. So what is cosine theta according to that right triangle? X over R. Now start playing. Multiply both sides by R. And do you see the R squared going, hello, hello, I'm a hypotenuse, I'm being squared. And then you go, oh, x squared plus y squared equals 2x. So do you know what this means it's going to graph? If I have a positive x squared plus a positive y squared, what shape will that be creating? A circle. I can figure out the exactness of the circle if I go through a completing the square process. Not going to do that right now. I just want to emphasize, though, based on this equation, you either have a circle or you have just a point, or you have something that is not visible in the real plane. So we know it creates some kind of shape. It must be a circle. What I want you to be aware of is if you don't have addition going on and you don't have any kind of multiplication with the theta, so no addition, subtraction, the only multiplication you might see is a constant multiplied to either sine or cosine. If that is your situation, you are drawing a circle. If you have addition with a number, it becomes a limaçon. If you have theta multiplying by something, then you have a rose curve. Now, that was that was this, and then we still have r equals 1. Now, I'm going to bring Desmos over because we need Desmos. And let me see, that is the graph of these two right here. And I'm going to snapshot of that. Now, if you're able to graph, you can also find intersection points. If you have a calculator, I mean. You can see the angles they intersect at. However, be careful because I doubt they would throw it to you in the middle of an AP test, but there are possibilities that it doesn't actually intersect at the angle it looks like it's intersecting at. The algebra trig work is needed to be sure. So the two functions were, and I already forgot. 2 cosine theta and r equals 1. So if I need to find out for sure what angles they intersect, I am going to set the two r's equal to each other and let trig take over. If I have unit circle and I am dealing with cosine, the special cosine numbers are positive 1 over 2, root 2 over 2, root 3 over 2, and negative 1 over 2, root 2 over 2, root 3 over 2, as well as x equals positive 1, 0, and negative 1. You have to be ready to deal with finding the angles for cosine of theta for any of those answers. 1/2 is this one. And what angles does that send us to? We've got pi over 3. And what angle would you write down over here? So this other angle is 5 pi over 3, but be very careful. If you set up an integral and you say 5 pi over 3 to pi over 3, realize that that is not giving you what you're thinking it's giving you. If I want if I want to find area that is created as I go from this angle to this angle, I have to make sure that that actually is making a direct route. So that is one of the biggest mistakes people make with polar area, is just putting down the unit circle numbers instead of recognizing the actual angular sweep that is creating that specific curve. So I just wanted to point that out because it is really, really important. Now, the original problem was asking us to find the area inside the first one. The first one was the black circle, yet outside the red circle. Can you figure out what region that would be that is inside the black circle, yet outside the red circle? And it's probably hard for you guys to actually write what you're seeing. So I'm going to shade it, and then you figure out if you got the right region. Inside the black, yet outside the red. Ooh, look, it's a crescent moon. So how are you going to set up an integral or a set of integrals that will give you that specific area? Do recognize that everything is taking place in between these two angles. Nothing goes outside of them. When you go about setting up an integral for area, I highly recommend that you draw spokes coming out of the origin or the pole. So if I integrate the black circle, then I am going from the pole, and I'm going to just draw lines heading out. I am going to get all of this area, which is more than I wanted. So I need the area in the black circle in between those angles, and then subtract from that the area inside the red circle, which I will create by integrating that red circle, or just finding the area of the circle and subtracting it. I should say the area of the sector. So let's think about what it might look like when I set up integrals that will find this, because again, multiple choice. They will likely give you an integral expression, and it may not be written the way you were thinking. You've got to be ready for a variety of ways that they would write it. So one option is you're going from negative pi over 3 to positive pi over 3. But realize another option is they might be looking from 0 to pi over 3 and doubling. And I'm going to write a 2 times 1/2 to make sure you're clear that that's what I'm doing, but you're not going to see anything there on a multiple choice answer. Here you're going to have a 1/2. Now, I am integrating, what were the equations? There we go. So first I want to integrate and find the area for 2 cosine theta. But I've got to remember the formula is 1/2 r squared d theta. And then I am subtracting from that. If this were to show up on an AP test, they would probably just find the area of the sector instead of the integral. Be aware of that. And yes, you can combine them into one integral because they are using the exact same angles. As long as they're using the exact same angles, you can combine them into one. So another option could be that you're doubling the area, and inside of one single integral, you are doing that. I'm not.
I mean, kind of like this, the setup of like subtracting.
Oh, yeah. Yeah. Just be extremely careful. The AP test is going to play games with you on this formula. Really think through every time you're setting up an integral for area, whether it be polar or rectangular. Think about what is creating it. Think about the formula behind it, and be careful because they love tricking you with the things that people normally trip over. Also, they often like to use area of circle instead of what I just highlighted. All right, now I'm going to take this same situation and I'm going to change it to find the area that is inside both. You're looking for area that is both inside the black circle and inside the red circle. And I'm going to erase what I have here. While I'm doing this, think about what is inside both. You want to make sure you are aware that the black circle begins at negative pi over 2. And when you're inside both curves, you want to be thinking who is closest to the pole. If I begin looking from negative pi over 2, and I draw little spokes coming out, I hit the black circle first. But then I get to that intersection angle, and it switches who I hit first on the way out. So it is very helpful to draw spokes coming out of the pole to visualize who you actually want to be integrating to find the area. And I'm going to make this a little bit more obvious. And then again, after I pass this intersection point, now it changes from the red circle being closest to the black circle being closest. Now, how about we just use symmetry? Just right away, let's use symmetry. So I'm going to put out a big giant 1/2 times 2 times whatever goes on here. It's just times 1, so I'm going to basically ignore it. All right. If I use symmetry, I am most likely going to deal with starting at 0. Starting at 0, I stop when I hit pi over 3 because things change. As I travel from angle 0 to angle pi over 3, which function should I be integrating? I should be integrating the red function. And again, the formula is 1/2 r squared d theta. I am then adding onto that area. When I start my integral back up at pi over 3, I change the function I'm following. And these two cannot be combined like we could combine them with the inside-outside. And I need to be aware that this black circle is sucked into the pole at pi over 2. And that's where you do need to be somewhat familiar with polar graphing. And then that function was 2 cosine theta? Yep. And yep, there we go. And I'm going to emphasize again 1/2 r squared d theta. All right, now, dun, 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 there is another graph I need to mention to you. Where did it go? Who was I? Now I forgot. Yes.
Do we have to divide the pi over 2 by 2 as well to get pi over 4? Or am I thinking? Like since you're dividing.
So what you want to keep separate from each other are angles are their own issue. And then the area formula is its own issue. The thing that is fastest to deal with is the area formula. The thing that you have to actually sit down and really map out are what angles do I need to put on that integral. That's what's going to really take you the time. And so when the symmetry comes in, you're just dealing with doubling the area formula. And that's it. And then that's changing. Instead of starting at negative pi over 3 and going to pi over 3, I'm starting at 0.
So it's only for that first integral?
It's for both. Because I found just this section, which if I double it, gives me both of these. And then for going 0 to pi over 3, that got me this area. And when I double it, that it adds in this area as well.
Okay, that makes sense. I got it. Okay.
Great. Okay, now I want to introduce you to something called a lemniscate. You may have used it before, back in a polar day of long ago. R squared equals 8 cosine 2 theta. R squared equals 8 cosine 2 theta. And I'm going to tell you right now, the lemniscates, they have R squared, and they always have either sine or cosine, and not any number times theta. It must be 2 times theta. Any number multiplied out there is just stretching it. So what I do is I turn this into ignoring that it's R squared. I find that I can deal with this best if I temporarily ignore the R squared and just graph my Cartesian thing. So if I have 8 times cosine 2x, the 8 just creates the amplitude, and then the 2 multiplied by the x squishes it. I'm doing my basic cosine graph. Normally I finish at 2 pi, but whatever x is multiplying by, I need to do the opposite operation to the x values, and I'm going out to pi instead of 2 pi. Now, I really need to know where r is equal to 0. So this r equals 0 is pi over 4, and this next one is 3 pi over 4. And there's something really important when I go back to r squared. The y values that I see on this graph are representing the answers to r squared. What do you see is kind of an issue? What is a very big problem? What can r squared not be equal to? If you just look at that, it almost makes you go, ugh. R squared cannot be negative. That means that the lemniscate doesn't graph on the real number plane while we travel from pi over 4 to 3 pi over 4. Now, if I go to the entire complex number system, my input variable is two-dimensional. My output variable is two-dimensional. That's going to create 4 dimensions, which I'm going to really need a computer system to help me even begin to understand that. But that is a big field right now in working with complex numbers, because even though we call it the imaginary number, it's not imaginary. It's just a different dimensional issue is really what it is. So anyway, you need to know that you do not want to integrate where the r squared is showing up as a negative value. And what I'm going to do, I love to graph from where r is 0 to the next time r is 0. I find that to be the easiest way to graph my polars. So I'm going to draw a negative pi over 4 line and a positive pi over 4 line. And while I'm at it, I also need 3 pi over 4 and 5 pi over 4. I will get one loop. Now, remember though, we're graphing the square root. So if I square root all these numbers, it's just going to kind of make it go, well, I'm just a lesser thing of what I once was. You rooted me down. So its highest value is root 8. So I'm just going to say that right there, that's root 8. 2 root 2, whatever you want to write it as. But I created a loop as I travel from negative pi over 4 back to pi over 4. Then I do not graph until I reach 3 pi over 4 and I do it again. It's supposed to be symmetrical. Then I don't graph, and then I do it again. There's a plus or minus issue involved as well, but all that's going to do is draw this same exact graph. So if you needed to find the area enclosed by a lemniscate, let me start off by saying the formula is 1/2 r squared d theta. If I integrate only one of these, then I'm going to double that. So I can integrate from negative pi over 4 to positive pi over 4. That will double my 1/2. I'm going to gently write 2 times 1/2. And then be very, very, very careful, because the function you have is already r squared. So r squared is 8 times the cosine of 2 theta. And integrating that will give you the area enclosed by the entire lemniscate. And you can see how you can use symmetry to change that. And how close to out of time am I am I already out of time? I was afraid of that. All right, so we are going to come back and deal with this head on on Monday after spring break, but you take a good week of a rest. You're not going to worry about turning anything in at this point. Just go have a spring break. Rest up, and I'll see you after that. I'm going to stop the recording.